All right, today we're going to talk about the phases of matter. And basically, the different phases, solid, liquid, gas, they have different energy levels. That's it. That's all you need to know. Write this down. This is important. So the first equation, we use that to calculate, whoops, that's supposed to be a K. We use that to calculate the energy, and sometimes it's called average kinetic energy. You'll see it as E sub K. But that's the thermal energy, or sometimes it's called the average kinetic energy. And it uses Boltzmann's constant. Boltzmann was a scientist, and he did a bunch of work. And so he has a constant. Just like there's a gravitational constant. And then there's Avogadro's number, which is the next one. But to calculate the energy per atom, based on the temperature in Kelvin, you use this formula. Okay. This 3/2 times the Boltzmann's constant. So let me point that out. So I don't know why they write the formula this way, but this is that 1.3 joules per Kelvin. Okay, and then this temperature has to be in Kelvin. Remember that to get Kelvin, you take whatever the temperature is in Celsius and add 273 to it. Okay. Now, I used to say Avogadro's number, like avocado. I used to say Avogadro. I always said avocado. It was really kind of funny, actually. I said it by mistake once. Then I said it as a joke. This is something that I like to do to my professors when I was in college. I would honestly mispronounce the name, then they would correct me very sternly because they're educated. And then I would pick up on the fact that they were a little slightly agitated with me, and then I kept mispronouncing it. I had one professor, I said Lagrange, and he said, it's pronounced Lagrange. He's French. And then I kept saying, are we doing that Lagrange thing again? And then the other one was Euler. It's spelled Euler, but it's pronounced Euler, again, French. And I would say, do we use Euler's method? It's pronounced Euler's. Eventually, he let it go. Anyways, it's Avogadro's number, and that's how many particles are in 1 mole. I use the word particles because it's kind of, I don't know. We usually use it to count atoms. And we'll talk about molar mass and atomic mass. The atomic mass of an atom is actually how much mass Avogadro's number is. That's how many particles are in that mass if you do the mass of an atom. And we'll go over an example of that in the notes. Okay. But basically, these are 2 important things we're going to use today. Make sure that you have them written down, star them, circle them, highlight them if you want. These are the numbers you're going to use for your homework today. There's a couple problems, not a lot. There's a lot of concept problems too. All right, can I move on to the next one? Okay. So don't write this down. I just want you to think about this. Let's say you're going to bake a cake or something, right? And imagine if the recipe called for 2 million grains of sugar. Wouldn't it make more sense to just measure a cup of sugar? So this is what we do with regards to that Avogadro's number. I already misspelled the word. Yep. Okay? So we would say 1 mole of a substance as opposed to 6.022 times 10 to the negative 23. Yeah? Yeah. Woo! Not negative, positive. Atoms. So you can see how 1 mole is like 1 cup. And, you know, this is very similar to 2 million grains, except it's way bigger. It's this big number right here. That's a lot of stuff. Okay? So a lot of times when chemists and chemical engineers, when they go to synthesize things, they don't do atoms. They just do molar masses. And it's that mass is usually in grams or milligrams or something like that, so they can measure precisely how much stuff they need to make stuff. Okay? All right, can I move on to the next thing? So chemists do the same thing here. It's easier to do 1 mole, all right? Again, you've already written this down, but I just want to highlight this. It's easier to say, well, I need 2 moles of carbon and 1 mole of whatever, sulfuric acid, and then you can convert that to grams. I need, you know, this many grams of this and so many grams of that, and then you can create chemicals, all right, and make molecules and do chemical reactions that way, okay? But remember that it's this many. This is the number that 1 mole represents, okay? 1 mole represents that, okay? And again, you don't have to write this down. You already should have it written down from the other slide. So I'm just going to move on. Is that okay? Okay. So hydrogen, now where the number comes from is that 1 mole is the number of atoms in 1 gram of hydrogen. So hydrogen on the periodic table, let me show you something real quick. So if I look at a periodic table, see this periodic table? If I click on that, see this number in the upper right-hand corner? That's the atomic mass. So if I click on this, that's the atomic mass, which is about 1. So where that number comes from is there's a number in the upper right-hand corner. Oops. Here. That is the atomic mass. Okay? So that would be 1 gram, which equates to 6.022 times 10 to the 23 atoms. That's why the number's so big. Okay? Any questions on that? Which is also 1 mole. Where's my little thing? It's not. There it is. So this also equals 1 mole. And I don't know why. It's kind of funny. They abbreviate mole to MOL. They drop off the E. Should probably just write the E. And then this number over here. So this is important. I'm going to change the color. It's not as important to us for what we're covering today, but remember, this is the atomic number. Also tells you how many protons are in it. Okay. Any questions so far? All right, let's move on. Everybody have this written down? So, individual atoms in a mole are too small for us to see. I do have some electron microscope pictures on some of my posters. If you're curious, after we take notes, you can get up and take a look at them. See what these actual molecules look like in different layers of things. It's kind of neat to see up close. But when millions of atoms interact, their average behavior is observable. And the most common things that we can observe is temperature and material. The temperature of the material, we could feel that with our hands. My coffee this morning, it was funny, it was very hot, and I poured it in the cup, and as I was my first drink, I could feel the heat hit my face. I was like, oh, wow, it was really hot. But also, we can observe the different phases, right? So if you think of water, water is the most common one. There's ice cubes, which is a solid. There's liquid water, which is just a liquid. And then if you boil the water, it becomes steam, and that's the gas. Okay? And this boiling of water occurs at 100 degrees Celsius, right? 212 degrees Fahrenheit. And I do probably should mention that it's 373 degrees Kelvin. Okay? And so we could observe that behavior. And then you say, well, Mr. Adams, what do you mean atoms interact to determine the temperature? Well, there's a relationship. As I add energy to this thing, as I add thermal energy to this thing, what it does is it increases the velocity of each one of these molecules. And so as they absorb that heat energy, one molecule flies out, and another molecule flies out, and another molecule flies out. And that's the steam. Oh, hold on. This is so weird. All right. Which is gas. Okay? Okay, move on. So then the temperature, this is important. You got to write this down. It'll help you with your homework. What is wrong with my little thing here today? So the temperature of a material is a result of the average kinetic energy. So this measurement is actually the temperature, right, which is also a measurement, an indirect measurement of the kinetic energy. Okay? And that relationship is the example that we had before, where that this is called the average kinetic energy or the thermal energy, which was 3/2 times kB, Boltzmann's constant, times the temperature in Kelvin. So here you have energy, right? I don't know what's wrong with this thing. And then you have the temperature. So that's the mathematical relationship between energy and temperature and energy. There's a mathematical relationship between the temperature of something and the actual kinetic energy it has, the average kinetic energy. Okay. So then you don't have to write down the example. We're not going to explore this too much, but a pot of water with the average kinetic energy of 7 times 10 to the negative 21 joules per atom is much hotter than 6 times 10 to the negative 21. It's not like 6 and 7. It's more like 70 and 60, sort of, but on the other end of the decimal scale. But how much hotter? It doesn't matter. Okay, did everybody can I move on to the next thing? All right, now you've already written this formula down, but maybe you should write these letters down and what they mean. So remember, E is the thermal energy per atom. this is Boltzmann's constant. Boltzmann was a scientist, did a lot of work on energy and temperature and stuff. He did a lot of physics. And then the temperature is always in Kelvin. And I should highlight, this is for gases only. Liquids, you do things a little different. So we're gonna. It's kind of like oh, how do I word this? It's kind of like friction in the roller coaster. You know, like we do the roller coaster, or we do the T-shirt launch, or we just kind of ignore friction for a little bit. We're just going to focus on gases. And they're very specific about calling this the average because in the universe, everything is dynamic. It will be very hard to find the exact kinetic energy at an exact moment in time. I mean, you can if you use calculus. But for most practical purposes, we would just do the average. And then think about that. There's 6.022 times 10 to the 23 atoms in 1 mole. Are they all going to have the exact same energy level? Are they all going to have the exact same temperature? Probably not. So this is just an average of all of those, of a very large number of atoms. Okay? I should point out that the constants, Boltzmann's constant, just like the gravitational constant, these are numbers, these are ratios that just kept showing up over and over and over again as they were collecting the data. Okay. All right, can I move on to the next one? Okay. So, I went too far. I don't want that there. But let's calculate this. Oh, shoot, I wanted to calculate it, but I forgot to delete the answer. So it says, how fast are atoms really moving, right? So we can figure out that velocity based on the energy, okay? So at room temperature, so we're going to say at room temperature, this is like 25 degrees Celsius, okay? And if you're curious, remember, in order to get Kelvin, hold on one second, let me just do this, 25 Celsius. Yeah. So it's actually a little warm, but I don't know why they do it this way. Where am I at? Over here. So remember that to get Kelvin, Kelvin is 273 plus Celsius. So that's where this 25 degrees Celsius comes from, right? And then also remember you can get Fahrenheit is equal to the 9/5 times C plus 32. So this temperature in Fahrenheit is about 77 degrees Fahrenheit. That's a little warm for room temperature. That's pretty warm. But that's what the book used. So I did this problem earlier, first hour, and I used like 72 degrees, which is closer to 20 degrees Celsius. And I got a different number, and it didn't match up with the notes. So I'm re-recording the videos. But this is what the book said, so that's what we're going to go with. So what I've calculated is that this is the average kinetic energy. This is the thermal energy, but it's also the average kinetic energy. While the kinetic energy depends on speed. So remember that your kinetic energy can be equal to, because energy just gets transferred to our thermal energy. So this is 1/2 times the mass, you should be writing this down, times the mass times the velocity squared. and then that's equal to this kinetic or average kinetic energy or thermal energy, right? So this is EK, and we'll call this EK. All right. So now if I do a little bit of algebra on this, I'll get a new equation. In other words, if I want to figure out how fast something is moving, I'm going to take this equation and algebraically solve for V equals some stuff. So I'm just going to do some algebra, move some things around, okay, and solve for the velocity, and then I can go from there. So does everybody have this written down? I can move on to the next slide. So if I do the algebra, I end up with this equation, okay? So if I rearrange that for speed, I end up with the velocity is equal to 2 times this energy divided by the mass of the object, okay? But we're talking about individual atoms. So this is the mass of one atom, sort of. Whoops, we gotta do some math on that. Whoops, I hate this thing. There it goes. Okay. So you will have, I think, 1 or 2 questions like this on your homework. It's a little bit, just plug it into Desmos. Make sure you plug it in correctly, though. Right? Okay, can I move on to the next slide? Okay. So now the next question is, how fast do you think helium atoms are moving inside of a balloon at room temperature? Well, I did this problem first hour, and I said room temperature was 20 degrees, and then the numbers didn't match up, and I was like, oh, yeah, they said that 25 degrees Celsius, which is 298 degrees Kelvin, is the room temperature. All right, so there's 2 things. I got to find this value here. Okay, so I'm going to say E to the K is equal to 3/2 times Boltzmann's constant, which is 1.38. You guys should be writing this down. Times 10 to the 23. It's negative 23, actually. Times the temperature, which is 298, right? And as you're writing that down, I'm going to plug this into the handy dandy calculator. So I have the equation 3 divided by 2. Holy moly. 3 divided by 2 times, oops, not this times Boltzmann's constant times 10 raised to the negative 23 times 900, or not 900, 298. And so I plugged that in on the calculator over here, and as you can see, it ends up being about 6.17 times 10 to the negative 21. Okay? So I'll write that down. And that's energy, so it's measured in joules. Now the mass is tricky, because I need the mass per atom, which is a very small number. What type of atom? Helium atom. So I'm going to have to go and look into this periodic table that I have here, and I'm going to look at the atomic mass. So if I click on helium, which is this little thing right here. No, that's neon. See that there? See that number in the upper right-hand corner? That's the atomic mass. Okay? So what I'm going to need to do is I'm going to need to use that number, which is grams per mole. So there's 4 grams per 1 mole. All right, so 4 grams per mole. So let's do that over here. So I need to convert that to atoms. So I have 4 grams, and where that comes from is on the periodic table. We looked up helium, and there was a 4 right there. 4 grams per 1 mole. And now I've got to convert that to atoms. Well, I know that I have to put 1 mole on top here. And we know that that is 6.022 times 10 to the 23, right? Atoms. Oh, I know what I did wrong. Okay, so I made a mistake there. Does anybody know what the mistake is? How do we measure when we use formulas? What unit of measure do we use for mass? Grams or what do we use? Kilograms. So I have to convert this 4 grams to kilograms. So there's a couple of ways we could do it. We could tack it on the end, and I have to have grams on the bottom. So I'm going to say grams here, but I know that there are 1,000 grams in 1 kilogram. All right, so that's a lot of multiplying. But remember, that's how we started this class. So grams cancels with grams. Remember at the beginning of the year? Moles cancels with moles, and I'm left with kilograms per atom. All right, so we got to plug that back into our handy-dandy calculator, which is right here. All right, let's see if we can do this. So I'm going to say 4. Well, wait, let me just do it this way. I'm going to say 4. Shoot, let's do this. On the top, I'm going to say 4 times 1 times 1. On the bottom, I'm going to say 1 times 6.022 times 10 raised to the 23rd times 1,000. And I get about 6.64 times 10 to the negative 27. Okay. Whew, that was pretty big. So my mass for 1 atom of helium is 6.64 times 10 to the negative 27 kilograms. All right, let's plug this in. So my velocity is equal to 2. Actually, it's the square root of 2 times this number. 6.17 times 10 to the negative 21 divided by this number right here. 6.64 times 10 to the negative 27 kilograms. And this is joules. then let's plug that in the calculator and see what we get. So I'm going to take the square root of, in parentheses, I'm going to say 2 times 6.17 times, whoops, 7 times 10 raised to the negative 21 divided by 6.64 times 10 raised to the negative 27. So it's about 1,363 meters per second. Okay? That's pretty fast. Does anybody have any questions on that? How do you feel about this? Thumbs up, thumbs down? Okay. Well, make sure you write all this down because you will have a homework problem like this, and you're going to have to calculate the energy, and you're going to have to calculate the mass per atom. And then in the mass per atom, you just, whatever, it's this exact same thing. The only thing that changes is this number, which you look up on the periodic table. And that's it. And if you have questions, so this homework is going to be the one where when I'm done talking, you got to do the homework now and then ask questions on how to do problem number 3 and stuff like that in order to get the homework done before the next time we meet. Okay? And then if you don't know how to do a problem, you can email me. But I suspect there'll be questions on this one because it's very algebra intense to get to the final answer, several steps. All right, and it's brand new to you guys. So ask the questions and we'll go over them together. All right, can I move on? Let's see if we're right. Duh. Get on my level. All right, that's pretty fast. Okay, that's 3,000 miles per hour. So the molecules, the helium molecules in a balloon are moving at 3,000 miles per hour, but they're just bouncing back and forth. And if you touch the balloon, you don't really feel it, do you? But millions and millions of those molecules are bouncing off of that rubber balloon or mylar balloon, whatever it is. So they have very high kinetic energy at room temperature. But room temperature, according to that problem, was 77 degrees, which is really warm. So let's talk about this. The 3 phases of matter, that's all you really need to write down. You don't have to be an artist and draw down the pictures or anything like that. Just write this down in your notes. You know it. You've been taught it your whole life. 3 phases of matter are liquid, solid, liquid, and gas. So solid, solid has the least, oh, I forgot, you guys don't know how to read cursive. Has the least energy, thermal energy. And this is the middle. And this has the most. Okay? There is one question at the end of this, and it's also kind of reworded on your homework where it talks about the thermal energy of these things. Now, ice, when you touch it, it feels cold. That's because it lacks energy, because the molecules are not moving as much in ice. When you have a cooler in the summertime and you go out to a picnic and you have a cooler and you have a bunch of beverages in the cooler and they have ice in there, the ice melts, right? But the beverages are really cold. What's really going on is that the kinetic energy in the beverage that was warm before you put it into the ice gets absorbed by the water molecules in the ice cubes. And then because it absorbs that thermal energy from the pop, what happens is that thermal energy causes the ice to melt. So the ice isn't really, it is cooling off the pop, but really the pop is giving its heat off to the ice. That's how that works. AC does a similar thing. At air conditioning, you have a coolant that just basically absorbs the heat and carries the heat out of a room. That's why if you have like the old school window air conditioners, does anybody have one of those in like their bedroom or something? The old ones that go in the window. Oh man, that was a 70s thing. So they didn't have central air back in the 70s when I was a kid. So you had like a air conditioner that you would put in your window. But anyways, it would blow the hot air. So inside the house, it would be very cold or colder. And then if you went outside on the back end of that air conditioner, it was just hot air coming out of the back of it. And all it was doing was transferring the heat from inside the house to the outside. Central air does the same thing. If you go out to the central, if you have like a heat pump or something, there's a fan, you'll feel hot air coming out. It's just pulling the heat out of the house. And when it pulls the heat out of the house, it cools off. And the coolant isn't actually cold, it's just it absorbs the heat and it just transfers it. It is cold though. It is cold. Anyways, can we move on? All right. So, two things. I want you to write this down. Inside, there are intermolecular forces. So, water it kind of has like polarity, and so these water molecules have an attraction to each other. Okay. Now, if they lack kinetic energy, they will layer right on top of each other and form ice, right? But if they have a little bit of kinetic energy, they have a tendency to want to move this way and move this way. So they'll pull apart from each other, but then the intermolecular forces kind of pull them back together. So they kind of oscillate like this. They move back and forth like this. So in solids, the intermolecular forces win. The intermolecular forces are greater than the thermal energy or the average kinetic energy of the molecules. But in a gas, they have so much thermal energy, they oscillate like this, but because they have so much thermal energy, they can break those intermolecular forces. And so that's why you have steam. And so the three phases of water, and it's really fascinating. There's a specific temperature, right? So water freezes at 32 degrees Fahrenheit or 0 degrees Celsius. If you go right above that temperature, you have liquid water. It's cold. At 33 degrees Fahrenheit, you have very cold water. But it's not ice. But if you go to 32 degrees, it's ice. And if you think of that on the Celsius scale, at 0 degrees, you have ice. At 1 degree Celsius, you have water. It's very precise. Same thing for the liquid water to become steam. At 100 degrees Celsius, it boils and starts to become steam. Okay? At 99 degrees, you have really hot water. Now, in reality, there's probably a couple of water molecules that are at 100, and some of them are at 99. So you might have one or two molecules jumping off, little pieces of steam you don't see. That's how evaporation works too. If you take a glass of water and set it out here and just leave it out here for days, eventually that water will evaporate into the air in the atmosphere. And that's a similar exchange, just air molecules blow over it. They have a little bit more energy, and there's like an energy transfer, and one molecule of water escapes. I just went to the Salt Flats in Utah. That's where I was over our little 3-day weekend. That was interesting too. The Salt Flats in Utah have dams. They soak up the water. It's not related to this, but it's kind of neat. They soak up the water. So in certain parts of the Salt Flats, there's little puddles of water. Kind of neat. I don't know. Anyways, also kind of random. All right, so in a gas, what happens is these molecules are still kind of attracted to each other, right? So let's say that this is attracted to this one, but also this one's attracted to this one. So these molecules are still attracted to each other. And, this one's probably attracted. Whoops. This one's probably, whoops. What in the heck is going on with this thing? There we go. This is attracted to this one, and this is attracted to this one. This might be attracted to this one or this one. So the purple ones represent the intermolecular force of attraction. The problem is that their thermal energy is much greater. So this thing is flying this way. This one is flying this way. This one's moving in this direction. This one is moving in this direction. This one is moving in this direction. Who knows where this one is going? And this one, let's say it's going this direction. So when they say that the intermolecular forces lose or that the thermal energy wins, that's true. There's more thermal energy, which exerts more of a force, more kinetic energy, and it breaks those intermolecular bonds. Okay? That's what a gas is. Now, a liquid, they tend to oscillate more. Okay? You don't have to write this down. Just think about this. In a liquid, they are stuck together. They still move. They oscillate like this within the liquid. In fact, sometimes they could switch neighbors. Okay, that's important. You might want to write that down. It's in one of your homework questions. So sometimes they can switch neighbors. So this water molecule is vibrating, and there's a bunch of water molecules, and they're all vibrating, and then they switch. It would be like if we removed the tables and I said, you guys just randomly walk back and forth. Well, there's a tight space in this room, and you might walk to your left, you might walk to your right, but it is possible that you bump somebody out of the way and you move to their spot. Does that make sense? But you're still confined to this room. Okay, so you can't really leave the room. A better example is if I tied a string to all of you guys. You can only go as far as the string lets you. That string represents the intermolecular forces. Okay, and in a solid, you fit together like Legos. Okay, you have no energy. Well, you have very little energy. So you don't even really oscillate that much. You do, though. I mean, there's energy in ice, right? So the molecules in ice do vibrate, but they don't vibrate as much. So a liquid is like this. A gas is like bing, 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 bing. A liquid is like this, swapping once in a while. A solid is like this. Okay? And so you're vibrating in place, but you have the same neighboring atoms. There's no switching. So write that down, no switching. You are locked in. Okay? It's like your seating chart in Mr. Adams' classroom. You could slide up and down in your desk, right? You can move around in your desk. You can move your hands. You can pull in. You can pull, but you're stuck to that seat. That's kind of how it works in a solid. Okay? We're almost done with the notes, by the way. All right. Can I move on to the next thing? Don't worry about this. Let's go on. So one other thing that you need to write down are these two sentences here. Intermolecular forces versus intra. Intra are the forces inside the atoms. Those are the ones that hold the molecules together, right? So when you think of a hydrogen oxygen bond, right? So this is water, this is H2O. There's something that holds those things together. It's a covalent bond, right? In other words, if I add heat to water, the steam is still water. That's an intramolecular force. The whole molecule moves around, but it's still water. This molecule isn't any different than one of these molecules here. This is still H2O. 2 hydrogen per 1 oxygen. And the same thing in the liquid. Let me see if I can find one. Yeah, this one here. This is still H2O. So those intermolecular forces hold the molecule together itself. Now, that just has to do with the attraction. Well, let me make that a different color. That's between molecules. So it's technically outside of the molecule. Okay, so that's the attraction between them. Now it says, which of these do you think is stronger? Well, the intermolecular ones are stronger, right? The intermolecular ones are not as strong as the intra, because it's still molecules of water at the end of the day. It takes a lot more energy to break those hydrogen. It's a covalent bond between the hydrogen atoms and the oxygen atoms. They share electrons, right? So intermolecular is stronger. Intra. I say it so fast it sounds like I'm saying inter, but it's intra. You guys look like you're done with school. Yeah, go. All right. This is just kind of saying the same thing. Let's do an example. So it says, write down this question. It says 10 grams of helium are at a temperature of 300 degrees Kelvin. We have 10 grams. What is the average thermal energy per atom? Well, the formula for that is E sub K is equal to 3/2 times Boltzmann's constant times the temperature in Kelvin, or make sure you write this down because there's a homework problem that's just like this. Times 1.38 times 10 to the 23rd times 300. And what about this 10 kilograms? Can I find out how many moles / atoms are in 10 kilograms? Yeah, but we don't need to. This is just extra. This is extraneous information. So we're not even going to use that. Because it's asking me per atom. So my math per atom is based on this equation. Now, if they wanted to know how much energy I had total, I'd have to, because this energy is per atom, I'd have to go back and, whoops, I don't want to do that yet. I'd have to go back and figure out how many atoms I have in 10 kilograms of helium, which is a lot. It'd be 2.5, I think, times, probably 2.5, well, no, yeah, 2.5 times Avogadro's number or something like that. But they're not asking that. They're asking per atom, and that's what this is. This is per atom. So then if we plug that in, you get this 6.21 times 10 to the negative 21 joules. I once had to do a problem for one of my physics classes in college where I had to calculate the entropy of the universe. And so I had to figure out the energy of it was a hard problem to do. Then I had to figure out how many of these atoms are in the universe, and yeah, it was a lot of multiplying. All right, everybody have that written down? Next one. You don't have to write this one down. This was kind of common sense. I'll just read it and you guess what it is. It says, Intermolecular forces in a certain substance are such that at room temperature atoms can switch neighbors, but are not completely separated. Completely separated would be what? Gas. Some of you guys went. What about switching neighbors? What would that be? That would be a liquid. And what about completely separated gas, switching neighbors? And then it says at room temperature, it must be in what phase? Probably the liquid phase if it could switch neighbors. If it is then cooled sufficiently to change the phase, it's most likely to be in what phase? Solid. Yeah, so the answer is liquid solid. Okay, that's it. All right, you have a homework assignment posted in Canvas.